So, last time we met, we finished talking about the limiting reagent. It's kind of been a while. Do you remember what the limiting reagent was? Can you say what you think the limiting reagent means in your own words?
It means something stops you from making something because you don't have enough of that one thing.
Very good. Give me an example.
Like if you want to make H2O and you have 15,000 oxygens, but only 4 hydrogens, you can only make 2 hydrogen waters.
That's right. If I have 4 hydrogens going into this, and I have lots of oxygen, 15,000 oxygens, right? Because I need 2 hydrogens for every water, and I only have 4, I'm only going to be able to get 2 waters. Very good. And that means I'm going to have excess oxygen. So what would be my limiting reagent under these kind of conditions?
Hydrogen.
Very good. Outstanding job. Okay, so looking at some problems, we can, and this is kind of an idea of how we find the limiting reagent, and we mentioned this last time. What you can do is you can set up answers for questions like we could say, how many waters equals sign, how many waters can I make if I have 15,000 oxygens? And then I can answer that question. And then I can do the same thing. How many waters can I make if I have 4 hydrogens, right? And then I can answer that question. And then I can compare these two and find out which one's less. And which one will be less? This one or this one? Yeah, this one will be less. That's right. And so I'll know that that is the true amount that I can make because it's less than this one. In this case here, we say, how many of these can I make if I have 4 hydrogens? But we're really saying, how many of these could I make if I had 4 hydrogens and plenty of oxygen? Right? That's what we're really saying, because we never have any information about how much oxygen we have here, so we're assuming we have plenty. This one down here, we're saying, how many waters can I make if I have 15,000 oxygen and plenty of hydrogens? So that's what that'll answer will be. But we won't have plenty of hydrogens, will we? So we can set up, in a limiting reagent problem, we can set up 2 of these answers, and the lesser one, the one that has the smaller amount, will be the correct, the actual amount that we can get. Okay? And we call that the theoretical amount. Theoretically, you should be able to get this much amount. Okay? So let's look at this question. Here I have a chemical reaction. Do you want to tell me the name of that compound? This is a good chance for naming a compound. Remind ourselves how to name compounds. What do you think? What's the name of that compound?
Calcium.
Uh-huh. What is the OH?
Hydroxide.
Very good. Calcium hydroxide. Excellent job.
Hydroxide.
So if I have calcium hydroxide, and this is hydrogen chloride, or if it's aqueous, it's called hydrochloric acid. And we'll talk about how we know it's acids in a different chapter. So we can just call it hydrogen chloride if we wanted to. But calcium hydroxide and HCl coming together, 2 HCls, I'm going to react those and produce 2 waters and 1 calcium. What's the name of this compound?
Calcium.
See if I can bring up my periodic table here. Element 17, right?
Oh, is that an L?
Yeah, Cl.
Not an L.
Uh-huh. Not an I.
Oh.
That's right, Cl.
Then it's calcium chloride.
Very good. Chloride, exactly. Calcium chloride. So the question is, when I have 1 gram of each reactant, what is the theoretical yield of water? And what is the limiting reagent? All right. Now, they told us here that this is a limiting reagent problem when they asked, what is the limiting reagent? But they won't usually be so kind in their questions in the exam. They'll just provide information and then say, what is the answer here? And you have to be the one that recognizes, hey, this is a limiting reagent problem. Okay? So how can we tell? How can we tell whether it's a limiting reagent problem? The way we can tell is because here they gave us an amount of not just one reactant. They gave us an amount of both reactants. Therefore, that means that unless they gave us the perfect amount where they're both going to run out at exactly the same amount, one of them is going to run out first. Usually, in the questions we've answered previously, they always say, if I have a certain amount of this material, some reactant, how much of this product am I going to get? But they don't ever mention about the other material because they just assume that we have plenty of it. But now when they've asked us how much product are we going to get when I mix 2 grams of material, then they're telling us that this is a limiting reagent problem. So we have to answer the question twice. And what is it we're looking for? The amount of what?
H2O.
That's right, the amount of water. And it doesn't say if it's in moles or grams, but we'll go ahead and put grams of water. And I wrote it twice because we are going to have to do it twice. One scenario, I start with 1 gram of the calcium hydroxide. And in another scenario, I start with 1 gram of the HCl. Okay? So I can go from grams of calcium hydroxide here to moles of calcium hydroxide. Now I went to the land of the moles. Why do I go to the land of the moles?
So you can just add up 2 and 2.
So I can get the power of the equation. Because this equation here tells me ratios of this material 1 to 2 to 2 to 1, but those are in moles. There's not in grams. So now I can go from moles of calcium hydroxide to moles of HCl. And then moles of HCl. No, sorry, not HCl, H2O. That's where I want to go, H2O. And then moles of H2O to grams of H2O. Okay? Can you help me with this? How many grams of calcium hydroxide are there per mole of calcium hydroxide? And usually they have the data on the chart to help us, right?
74.
Yeah. Whoops. 1 mole of the stuff is 74 grams. All right. How many moles of, this is supposed to be water here. Let me rewrite that above. H2O. How many moles of water for every mole of calcium hydroxide?
0.
Let's see. Where do I get that information?
1.
The moles of what? Calcium hydroxide or moles of water?
1 hot water equals 1 C.
So here I have moles of water on top and moles of calcium hydroxide on the bottom. And that, the numbers that go here are going to be the relationship here in the equation. 1 calcium hydroxide for every what?
2.
waters. Very good. Way to go. Excellent. And now my last one here relates the moles of water to grams of water. What's that? How many grams per mole? Should be down here on the bottom.
18.
Very good. 18 grams per mole. Fabulous job. So the calculator needs to come out. I need to multiply my, where is my, there we go. I got 1 gram here. 1 divided by 74 times 2 times 18. And that tells me 0.4865 grams of water. Is that the answer?
For one question.
Yeah, but we have to do the other one and find out if it's more or less. All right, so I go from grams of HCl to what? It's my favorite place besides Disneyland.
Land of the moles.
That's the land of the moles. So I go from grams of HCl to moles of HCl. All right, and then I go from moles of HCl. Now that I'm here at the land of the moles, I can take advantage of the power of the equation, right? And convert moles of HCl to moles of water, right? What's that relationship?
That's 2 to 2.
2 to 2. Very good. 2 to 2. Or I could have just put 1 to 1. Same thing though, right? All right. And now I'm going to go from moles of water to what?
Grams of water.
Grams of water. And what is that in value?
18 and 1.
Very good. 18 and 1. Out comes the calculator. 1. Uh-oh, we didn't fill in this information.
36.5.
5. Good. 36.5 grams per mole. So 1 divided by 36.5 times 2 divided by 2 times 18. 0.493. Okay, so what does that tell us? What have I learned?
That you can figure out which one is the limiting number now.
Very good. I can tell which chemical is the limiting reagent. That's right. Which chemical is the limiting reagent?
The top one.
Very good. Calcium hydroxide. That's the smaller amount. So this is the limiting reagent. And this is my theoretical yield. Because this is the one that's going to run out, this tells me how much I theoretically should be able to get. Theoretically means if everything goes right, this is how much you should be able to get. Okay, very good. So calcium, or 0.4865 is my theoretical yield, and calcium hydroxide is my limiting reagent. Okay, I'm going to let you guys practice this one here. How many grams of NO can form when 30 grams of this and 40 grams of that react according to that reaction? Okay, I'm going to let you guys practice. These are the models, kind of sloppy here, but you followed along hopefully so you know what to do. And let's see if you guys can do it. All right, I'm going to show you the answer here in 2 seconds, so make sure you push pause and take a stab at it. Ready? 1, 2. Okay, very good. So what we learned here is if we start with 0.176 moles of ammonia, we get 0.176 moles of nitric oxide. If we start with 0.125 moles of oxygen, I only get 1 mole of nitric oxide. So the limiting reagent then is the oxygen gas, and 1 mole of NO, down here it says, is 30 grams of NO. Now I got these 1.76 moles of ammonia by taking the 30 grams and converting it to moles. And I got the 1.25 moles of oxygen gas by taking the 40 grams and converting it to moles. Excellent job. Okay, here's another one. We had 2 practices. This one's all by yourself. So go ahead and do it at home. I'm going to give you 2 seconds, and then I'm going to go ahead and push pause and do it. But we're going to let them practice this one. Okay, 1, 2. Okay, so here's the answer. So 0.9 grams. All right. Hope you got that one. This one's kind of hard here because you don't have a chemical reaction necessarily, but you can see that the number of the elements, the number of mercury ions, 2 here, the number of nitrate ions, 2 here, relates to the number of mercury ions and the number of chloride ions and potassium chloride here, so forth. So you kind of have to look at this one without an equation and try to figure out what your relationship is. Now we're going to talk about what we call actual yield. Actual yield. Oftentimes when we perform a chemical reaction, we don't actually get as much as we think we're going to get. And that can happen for a lot of different reasons. It's kind of like when you make cookies. Did you know usually when you make cookies, on the recipe it says this many cups flour, this much butter, this much sugar, this much salt, and then in the end it says this should make 24 cookies, or this should make 36 cookies. It's telling you how much it should make. And that is like a theoretical yield because it's telling you how much it should make. But then actually, how much it actually makes is a completely different story, right? Sometimes the cookies are bigger or smaller. Almost always, though, it never makes as much as it says it's going to make. And so the actual yield is different than the theoretical yield. For chemistry, the reasons why the actual yield might not be the same as the theoretical yield is because the chemicals might stop reacting after a while. The product might stick to the glassware, or some material might be lost as you're stirring or on the stir bar, or maybe in the filtration device or whatever your purification step was. So it's very common to not get exactly how much you think you're going to get in your chemical reaction. And so we have what's called, again, the theoretical yield. That's how much you should get, but the actual yield is how much you do get. And then the actual yield over the theoretical yield. So if I take the actual yield and put it over the theoretical yield, and then times it by 100, that gives me what I call my percent yield. Okay? So here's an example. A cookie recipe predicts a yield of 36 cookies, and yet only 24 are obtained. What is the percent yield? How would I solve this? What do you think? You there, Tom?
Yeah, he fell asleep, so I'll try to answer it. I think you asked how you get it. So you divide how many cookies there were by how many they were supposed to be.
So what's that? What goes on top?
24 divided by 36. 24.
What? 24 divided by 36?
Yes.
Okay, 24 divided by 36. That gives me 0.66. Is that the right answer?
Yeah, you times it by 100.
Okay, good. Then you times it by 100. Very good. So 66% is my what?
Percent yield.
Percent yield. Very good. Excellent job. Okay, here's a crazy one. Do you think you can answer this one?
Wow.
When 6.4 grams of methanol is mixed with 10.2 grams of oxygen and ignited, 6.12 grams of carbon dioxide was obtained. What was the percentage yield of the carbon dioxide? So, what do I got to do to answer this one?
He just woke up. Let me give you back to him.
All right, so let's give everybody a chance at home to work on this one. All right. What we need to do first is we need to find the theoretical yield. We need to find out how much we theoretically should be able to get given the 6.4 grams of CH3OH and the 10.2 grams of oxygen. All right. Now, this is a limiting reagent problem. So after we identify how many grams of carbon dioxide we expect, right, for each of those, the 6.4 grams of methanol and the CH3OH, that's methanol, and the 10.2 grams of oxygen, after we identify that, then we should be able to find which one is the least, and that'll be our limiting reagent, right, our limiting reagent. And then once we have our limiting reagent, we should be able to find out theoretically how much we should get. And then we see that we actually got 6.12 grams. Okay, so go for it. You try it at home, and I'm going to, after you're done trying it at home, I'll show you how to do it, and then we'll see what the answer is. Okay, 1, 2, I'm going to start trying, I'm going to start doing it, okay? I need to find, and remember, it's very important that you follow the pattern so that you can guide yourself through this sort of a question. Okay, so I'm going to find, I'm going to write 2 of them to remind myself that I have to do it twice. It's a limiting reagent problem. But I'm going to find how many grams of carbon dioxide I theoretically should be able to get. Grams of carbon dioxide. I wrote it twice again because I'm going to start here with 6.4 grams of methanol. And here I'm going to start with 10.2 grams of oxygen. 6.4 grams of CH3OH goes to moles of CH3OH. And then moles of CH3OH goes to, I've got to go to carbon dioxide, moles of carbon dioxide. And then moles of carbon dioxide goes to grams of carbon dioxide. I remember this, 44 grams per mole. The molar ratio here, oops, this isn't 6.4, sorry. The molar ratio here, carbon dioxide to methanol, is, do you see it? What is it?
Carbon dioxide. Wait, dioxide's that one, yeah. 2.
2 carbon dioxides to how many methanol?
Methanol. What's the letters?
CH3OH.
2.
Yeah, 2 to 2. Very good. And then 1 mole of methanol is, it's telling us down here what the molar masses of all these are. So it's 32. 0.04. All right. So, you have a calculator nearby?
No.
Okay. I'm taking this calculator. When you get a calculator, why don't you try this one here? And while you're trying that one, I'll work on this one. Okay, so we go from grams of oxygen to the land of the moles, moles of oxygen. And then I go moles of oxygen to moles of carbon dioxide. And then I go moles of carbon dioxide to grams of carbon dioxide. 44 grams per mole, I remember that. 32 grams per mole of oxygen. And the ratio of carbon dioxide to oxygen is 2 to 3 in my stoichiometry up there in my chemical equation. All right, so I'll work on the bottom one while you work on the top one there. 10.2 divided by 32 for me, times 2 divided by 3 times 44. All right, so I got 9.35. grams of carbon dioxide. What did you get? Did you get
8.8.
8.8 grams of carbon dioxide? So what does that tell us is the limiting reagent?
The top one.
Yeah, the methanol, CH3OH. Very good. And this becomes what? What do we call that value then?
Limiting reagent?
It's the theoretical yield. The theoretical yield.
Oh, yeah.
Theoretical yield. Now, how do I get the percent yield from the theoretical yield?
Divide by 100 and then times by 100?
I take the how much I actually got, which is 6.12. 6.12 grams of oxygen or carbon dioxide was how much was actually obtained. So I take that 6.12 divided by the 8.8 and then times by 100. And that'll be my percentage.
69.5.
All right. Is that one of the answers? It's pretty
Yeah.
close, right? Very good. 69.6%. All right. Outstanding job. Wonderful. That's it for chapter 4. We get to move on to chapter 5. How exciting. See you next time. Bye-bye.